Hi class, today we're talking about composite functions. And composite functions are written in a special way. They're written as f of g. And we say f of g or f composed with g. You wouldn't say dot because dot means something else. And be also careful when you write it, you don't want to write dot because that means multiply. But we want to do the little open circle. And we would say f of g is our composed function, and we're going to put in our variable of the function. Typically, our variable is going to be x. Now, the definition of f of g of x is that you take x and you plug it into g of x to decide what your new value is, and you take that new value and you plug that into your f function. And you might notice we're going backwards as into the way we plug it. We're going to take the x and substitute it into my g function, take that result, substitute it into the f function. And let's just do one, for example. Here I have two functions to find, f of x and g of x. And if I wanted to find f of g of x, well, that means I'm going to take my x and plug it into each of those two functions in that order. Let's take a value such as 4 and plug it in to my function. Well, what that really means is I'm going to take f of g of 4, and we're going to simplify the part in here first. So what I want to do is plug that in 4 into g. I'm going to do it here on the side. G of 4 is going to be 4 squared minus 2, so 16 minus 2, so I get 14. And so now I'm going to replace g of 4 with its value 14. And then I'm going to evaluate this, which is, and I'm going to evaluate f of 14. So I'm going to get the square root of 14 minus 5, which is the square root of 9, which is 3. So notice that I had to figure out that g of 4 was equal to 14 and replace that value in my function. And so that I'm trying to find f of 14. When you're working on this, sometimes you might be tempted to plug the 4 into the f, and we don't want to do that. We want to plug 4 into g, evaluate that, and plug that evaluated value into our f function, and then that's how we solved to find 3. Let's get some practice at doing this. Our first question asks us to find f of g of 0. And I'm going to take the definition and rewrite it as f of g of 0. Now I'm writing it in a new color just because I want us to focus on that inner portion. This is my g function, the upper function that got graphed. So g of 0 would be the point right here on the y-axis. That would be 0, 5. So I'm going to replace, well, I'm going to write my function, and then I'm going to replace the g of 0 with 5, because we know that g of 0 is equal to 5. And then I'm going to take a look at the f function, and the f function is the lower one. And so when I want to find f of 5, I can see that it's on the graph. F of 5 is equal to 1. And so f of g of 0 is also equal to 1. Let's try that again with question number 2. It asks us to find f of g of 2. And once again, I'm just going to use the definition to rewrite that as f of g of 2. And I'm going to look at the g function at 2. I actually have the value 2. So I'm going to replace g of 2 with the value 2. And I'm going to plug that into my f function. Looking at my f function, I have the value of negative 2. And so that's what the value of f of g of 2 is. Once again, remember that we're plugging the 2 into the g function first getting that result and plugging that result into the f function. Question number 3 is different from the first two because we're actually asked to find g of f of 5, meaning that if I use the definition, I'm going to take g of f of 5. And so we're going to take the 5 and plug it into the f function first. And that gives us a value of 1. So I'm going to replace f of 5 with 1. And I'm going to now evaluate what's g of 1. Looking at that function, I get the value 1, 4. So g of 1 is 4. Therefore, g of f of 5 is also 4. You need to practice this so you remember which direction to plug it in. We don't go in order from left to right. We go from inner to outer. And so we take it and we go from right to left. The 5 goes into the f first. That result goes into the g function next. Now for question number 4, it's asking us to do several compositions. However, for the first two compositions, we're not being asked to plug in values. We're actually just asked to find the composite function. And that can get a little bit confusing. So what I did is I highlighted f of x in orange and I highlighted g of x in blue so that you can sort of follow along a little bit better. I'm also going to take this function and rewrite it using the definition. That means I want to find f of g of x. Now remember, f of g of x is my blue function. I'm going to replace my blue function with 2x squared minus 1. Now I'm going to write f of x as 3x plus 2, but I'm going to replace the x with parentheses. Keep in mind that the 3x plus 2, or the 3 parentheses plus 2, is my f function, and now I'm going to input my g function into the parentheses. Now that I have my g function written as the variable inside my f function, then I can simplify. So I'm going to get 6x squared minus 3 plus 2, and that becomes 6x squared minus 1. So f of g of x is 6x squared minus 1. Let's move on to the next question. It says, what is g of f of x? And order does matter, so this is not going to be the same answer as before. Now, I'm going to say I want to find g of f of x using the definition that we were given. And keep in mind that my inner function now is f of x, whereas the previous question had the inner function be g of x. I'm going to rewrite this. So I'm going to get g of, and I'm going to replace f of x with what it's equal to, which is 3x plus 2. And once again, that was my orange function. Now I'm going to take my g function and I'm going to write 2x squared minus 1. Keep in mind that this is my blue function because that matches the g function. But inside my blue function, I want to plug in my orange function. So I'm going to plug in 3x plus 2 into my parentheses. And now that I've written it in there, I need to simplify this. Now, we have to follow the order of operation, so I need to do the exponents before I do the multiplication. So I'm going to get 2, 9x squared plus 12x plus 4 minus 1. Now I can multiply that out. So I'm going to get 18x squared plus 24x plus 8 minus 1. And then simplify one more time to combine like terms. And g of f of x is 18x squared plus 24x plus 7. F of g of negative 2 can actually be done two different ways. So I'm going to do it the first way that we practiced last time, which is f of g of negative 2. Now I simplified g of negative 2 and I found out that g of negative 2 is 7. So when I'm writing this, I'm going to replace the g of negative 2 with 7. That's because I did all the work up here. And so I'm going to replace that. Now f of 7 is something I know how to do. That would be 3 times 7 plus 2, which is 21 plus 2, which is 23. Now, this is the steps that I took last time to solve it. However, I want to point out that we did find out what the f of g function is. You can see that we simplified f of g of x to be 6x squared minus 1. Let's use that definition now. If I say find f of g of negative 2, well, I know f of g is just 6x squared minus 1. Is it possible that I could just plug in negative 2 into that? Let's try. We got 6 times 4 minus 1, which is 24 minus 1, which is, hey, I get the same answer as before. I get 23 as my answer. So you can go through the steps of plugging negative 2 into g and then plugging into f, or you could just plug it into your f of g function and you would get the same answer regardless of which way you go. Let's get some more practice doing this with question number 5. F of g of 4 can be written as f of g of 4. And g of 4 could be simplified as 3 times 4, which is 12. So I'm going to say, instead of f of g of 4, I'm going to get f of 12. Now that's fairly easy to do. So we're going to take 12 and plug it into the f function. That's the square root of parentheses plus 1. Inside of that, I'm going to write 12. And I get the square root of 13 as my answer. That's okay. Let's go ahead and see what f of 1 is. Well, that's going to be f of 1. And so let's see what f of 1 is. I'm going to write that over here. F of 1 is the square root of 1 plus 1, so it's the square root of 2. So I'm going to say, let's take f of, and I'm going to replace f of 1 with radical 2. Now let's take that and plug it back into the f function. The f function says the square root of x plus 1. The x in this case is now going to be radical 2, which I don't know how to simplify that. I'll just take the parentheses out and leave it like that. So f of 1 is the square root of 2 plus 1. And since you can't simplify it, we'll go ahead and leave it like that. F of g of x is going to be f of g of x. I'm going to write f of, and instead of g of x, I'm going to write 3x, because that's the function. Instead of f, I'm going to write the square root of parentheses plus 1. Inside my parentheses, I'm going to put 3x. And I can't simplify that anymore, so I'm just going to say the square root of 3x plus 1. And so we simplified each of these. With the ones that have numbers plugged in, f of g of 4, we got a value like radical 13. But for the composition of functions, that's f of g of x, you're just going to get a new function, which is the square root of 3x plus 1. I want to find f of g of x, and I want to find the domains for this next question. But first, let's find the domains of f and g individually. First of all, we can see that the domain for f of x is x cannot be equal to negative 3. And the domain for g of x is x cannot be equal to 0. When we look at the composite function, we have to take into account how the composite function was constructed. So we're going to say f of g of x recall that this means we're going to plug g of x into f. So everywhere that I write g of x, I'm going to highlight it in light blue so we can distinguish it from the f function. Now the f function says 1 over x plus 3. Now all of my x's I'm going to replace with parentheses, and then I'm going to stick my g function inside those parentheses. So you can see that I have a fraction inside a fraction. And so all we need to do is simplify this. We simplify by multiplying by the LCD. In this case, the LCD of the little function, or the g function, is x. That's what the denominator is. So we're going to multiply the numerator and the denominator by x. So I end up with 1x in the numerator. And I'm going to get negative 2 over x times x plus 3x for my denominator. The x and the x will cancel out. That's why we chose this. And so I'm going to be left with x over negative 2 plus 3x. Now that's our composite function. Now when I look at this f composed with g, I notice that there is a variable in the denominator. So in order for me to find the domain, I want to set that not equal to 0. And so I'm going to say that my domain is 2/3. Or my domain is all of the real numbers that is not 2/3. Now, there's a problem with saying this is my domain. If this were my original function, then that would be great. I could say that's my original function, this is the domain that goes along with that original function, and that would be completely fine to say. However, if you look at the actual original function, it was written with a fraction inside a fraction, and we have to pay attention to that. The little g function is inside of here, and we have to make sure that that little function is also valid. So we have to make sure that we don't plug in x equals 0. So that also has to be taken into account. So there's actually two numbers that cannot be in my domain. Now technically, if I plug 0 into this function, I would get a value. However, if I plug 0 into this function, it doesn't work. And so even though they look like exactly the same functions, they have different domains, and we have to pay attention to the way that this domain was constructed, and we have to throw out the x equals 0 as well. Let's try this again by composing g with f. For g of f of x is my inner function, so we have to pay close attention to the domain of that f function. I'm going to write my g function as negative 2 over parentheses, and inside those parentheses I'm going to write f. F is 1 over x plus 3. To get rid of my fraction within a fraction, I'm going to multiply this whole fraction by the denominator of the other little fraction, which was x plus 3. And when I do that, I get negative 2 times x plus 3 over 1 over x plus 3 times x plus 3. And so these ones will cancel out. However, I was to have the negative 2 times x plus 3 over 1. And so I just get negative 2 times x plus 3, or negative 2x minus 6. Now it looks like this is a polynomial, and it looks like it doesn't have any denominator anymore. And technically the domain for polynomials is all real numbers. However, we have to take into account how we first wrote this, and it was with a fraction inside a fraction. And that little fraction had the domain that was x is not equal to negative 3. So we have to remember that that has to stay true no matter what. And so my domain here is going to be x is not equal to negative 3. That's the domain of g of f of x. Our next two functions that we're going to compose are f of x, which is x squared plus 4, and g of x, which is the radical of x minus 2. And the domain of the polynomial is all real numbers. Well, let's work on the domain of that radical. In order to have a radical, the radicand must be positive or 0, So I'm going to say that the inside of that radical has to be greater than or equal to 0. And then we'll solve that. And let's go ahead and write it in interval notation. So written in interval notation, that would be 2 to positive infinity, including the 2. Now f of g of x, which once again we know is f of g of x. To write this, first we will write the f function with parentheses replacing the variable. So I'm going to say parentheses squared plus 4. And then to plug in our g of x, we're going to write our g of x, which is the radical x minus 2. And now that we have it written out, let's go ahead and simplify. So the square root and the square will cancel, and so I would just end up with x minus 2 for this portion, and then we'll add 4. And then we can just say that is x plus 2. And that looks like a polynomial. Now f of g of x is x plus 2 when it's simplified. However, we once again have to take into account how this was made. And if you look at the original function, when I first plugged g of x into f, it's not as simple as that. It is the radical x minus 2 squared plus 4. And so for this one, we have to make sure that we take into account this domain over here. And so that's going to be the same domain. Okay, now let's move on to g of f of x. Now with g of f of x is our inner function, and we're going to plug that function into g. So recall that the g function is radical x minus 2, and notice where the parentheses goes, it replaces the x, and inside my parentheses I'm going to put my f function right here. And so my f function is x squared plus 4. And let's see if I can simplify this any. I'm going to say that's x squared plus 2 inside the radical. Because I have a radical, we want to say that the radicand has to be positive or 0. So that radicand is the x squared plus 2, and it has to be positive or 0. And when I say x squared has to be greater than or equal to negative 2, when is that true? Well, x squared will always be positive, and a positive is always greater than negative 2. So this domain is going to be all real numbers. So my g of f of x is simplified to be radical x squared plus 2, and my domain is going to be all real numbers. Let's look at how it was originally built. F is on the inside, and the domain of f was all real numbers, and so that still holds. This last question asks us that, well, it gives us a function that it says can be a composite function, and it wants us to break it down into the pieces where it came from. Now, one thing to know is that you can build this function in multiple ways. But before we start doing this, I want to recall how we've been building our composite functions. I've been telling you to replace your variable with parentheses and then fill in the parentheses with the inner function. Basically, we're going to use parentheses to do this. So one of the ways that we break apart a composite function is to look for good places to put parentheses that hold the variable in it. Now for this question, it actually already has parentheses in it, so that could lead us to one of the easiest ways to break this down. If I use this set of natural parentheses in the question to designate the inner function, then my g of x will be that inner function, and then I'll replace everything I highlighted with my variable for my outer function. That is, my outer function will be that parentheses turns into my variable, and my inner function will be everything inside that parentheses. And if you compose them together, then that makes h of x. However, I want to point out that that's not the only way you could have done that. I'm going to set another set of parentheses and see if we can replace it with our variable. For example, what if I put my parentheses around the x squared? Well, let me highlight that. In this case, we could call our inner function x squared. And then we're going to replace that parentheses with x for our outer function. And I could say 1 plus my variable cubed. Now these aren't the only two ways I could break this up. There's other ways you can do that. However, you do want to keep in track of places where you can put parentheses without changing the meaning of the sentence, and also the fact that all the variables have to be within that one parentheses that you put. So once again, we did this question in two different ways. Both of them would be valid answers. When you look at this question, try to be creative. Try to come up with more than one solution to breaking it apart into pieces and seeing if you can understand composition of functions better by putting your parentheses in places where they make sense, and by taking the inner function and the outer function as f of x and g of x, so that you can build some creative composition of functions.